Hello everybody. In this video we're going to find the area under the curve y equals x squared. So the plan is that we're going to take the curve y equals x squared and we're going to determine the area of the region lying below the curve, above the x-axis, and between the vertical lines x equals a and x equals b. To make our job easier, we're going to need a little tool, and that tool allows us to find the sum of squares. So here's a formula for this. Suppose you want to take, say, the first n squares, 1 squared, 2 squared, 3 squared, all the way up to n squared, and you want to add them together. Turns out there's a slick formula for this. It's this cubic polynomial, n times n plus 1 times 2n plus 1 over 6. Now we're not going to prove this in this video. We'll just make sure this works in a couple of cases. So let's take the simple case of n equals 3. We'd be looking at the sum of the first 3 squares, 1 plus 4 plus 9, which turns out to be 14. And if we look at this formula on the right side and substitute 3, we're going to get 3 times 4 times 7 all over 6, which simplifies to 14. So the formula works in this case. And we could try another simple case like n equals 5. So we'll take the sum of the first 5 squares, and this winds up equaling 55. You can do this by brute force. And when you substitute 5n for n in the formula, you get 5 times 6 times 11 over 6, which is clearly 55. So once again, the formula works. So we'll just take it as a given that this formula works for all n, and we'll use it as we need moving forward. Now suppose we wanted to approximate this area under the curve of some function f. Well, one way we could do that is we could use a bunch of rectangles. So any way you can manage to tile rectangles on in a way that you think approximates the area, rectangles are something whose area we can calculate relatively easily. It's just base times height. So if we can find appropriate rectangles, maybe we have a chance of approximating areas under graphs of functions. Now let's go back to our curve y equals x squared. Here's a problem. Find the area A enclosed below the curve y equals x squared, above the x-axis, and between 0 and 1. So I want to emphasize here that we are restricting our attention from the original problem just to a smaller problem, which is finding the area under the curve just from 0 to 1. And it turns out we're going to put a lot of work into understanding this one special case. And you might think, well, that doesn't bode well because that's just one very special case. But in fact, if we can figure out the area from 0 to 1, things are really going to move quickly and we're going to be able to figure out the general formula. So let's concentrate on this problem first. We're going to estimate the area using rectangles and see if we can draw any useful conclusions. So how could we do this? We could say divide the interval into 5 equal subintervals. So we have the interval from 0 to 1 divided up into 5 equal pieces means we should choose our endpoints of these subintervals to be at 1/5, 2/5, 3/5, 4/5. And then we're going to rewrite 1. It'll be good to think of it as 5 over 5 moving forward, and you'll see why. So we're going to evaluate the function at right-hand endpoints of each subinterval in order to find the heights of the rectangles. So what are these heights explicitly? Well, this height would be 5 over 5 squared, and the next one would be 4 over 5 squared, 3 over 5 squared, 2 over 5 squared, and 1 over 5 squared. These are the heights we're going to use. Now, the widths are all the same. The common width here is 1/5. So moving from left to right, our areas, or the area of the first box, will be 1/5 squared times 1/5. The next box will be 2/5 quantity squared times 1/5, and so on. And we'll move right across to get the 5 rectangles, and we've calculated all those areas. And now we have an estimate for the area we're looking for. Let's do some algebra here. We'll notice that there are plenty of factors of 5. And in fact, there are 3 factors of 5 in each term. So we'll pull out 1 over 5 to the third, and that leaves a simple sum of squares. And we actually calculated that a moment ago. So it's going to be 55 and then 125 in the denominator. So here we have the combined area of these 5 rectangles is 0.44. And we're going to call this a right-hand sum with 5 divisions. The 5 is pretty obvious. We've chopped it up into 5 pieces. And the right hand refers to the fact that we're using right-hand endpoints within each subinterval to find the heights of the function. So we would say that the right-hand sum with 5 divisions here is 0.44. Now, what does the general sum with n subdivisions look like? In other words, we're not going to specify the actual number of divisions. We're just going to assume it's n. How can we calculate this? Well, first of all, the common width of each subinterval will be 1 over n in that case. And we'll have to move from 0 that far each time to find a new endpoint. So the arguments in question are 1 over n, 2 over n, and so on, all the way up to 1, which once again we're going to write as n over n. Let's think about a generic box. So the width is 1 over n, and we're going to look to the right, and suppose that endpoint there is k over n at the right side. So this height would be k over n quantity squared, and then the area of that rectangle would be k over n quantity squared times 1 over n. So this is sort of the generic area, and we're just going to add a bunch of these together. So you should convince yourself that this is what the formula looks like, and you can just check various aspects of this formula. So there are n terms, which you expect. Each has width 1 over n, as far as thinking of it as the area of a box, and each height comes from taking the right hand side of the interval, taking that argument and evaluating the function there. Once again, there's some algebra we can do. There is a common n cubed throughout, so we're going to factor out the n cubed in the denominator. And here's our opportunity to use our sum of squares formula. So we know we have a formula for this. It's going to be n times n plus 1 times 2n plus 1 over 6. We'll just draw the n cubed underneath the denominator there, and now we have a nice general formula for a right-hand sum. So let's just take this for a test drive. If we were to divide up the interval into 15 pieces, according to the formula, you're going to get about 0.3674. And if you chopped it up into 60 pieces, the formula is going to give you the value of about 0.3417. Now, what's happening as n goes to infinity? Let's try to understand what this formula is telling us as we let n grow larger. So we know that for all n, the right-hand sum is going to be larger than the area we're trying to understand. So we have this inequality that the right-hand sum with n subdivisions is always greater than a. The right-hand sums overestimate the actual area for this function on this interval. Please don't think that right-hand sums always overestimate the actual areas. It's only true in this case because the function in question is strictly increasing on the interval in question. Now, if we plot the right-hand sums as a function of n, you're going to get a picture that looks about like this. And let's start listing some facts. We just saw that the right-hand sum with n divisions is always greater than the actual area. So if we were to plot a horizontal line at the value y equals a, we know that it should come in below every point on this graph. And this formula, we'll notice, has in the numerator a cubic polynomial with lead coefficient equal to 2. In the denominator, we've got a cubic polynomial with lead coefficient equal to 6. So what happens here is the ratio, the right-hand sum formula, actually tends to 1/3 as n goes to infinity. So we're going to write that up here. The limit as n goes to infinity of RHS of n is 1/3. So we'll plot the horizontal line y equals 1/3 here, and notice that it is a horizontal asymptote of this graph. Now, this sequence of terms, this function is strictly decreasing. And we're going to leave that as a verification to the viewer. So you can either take the derivative and show that the value is negative on the interval in question so that this sequence of values has to strictly decrease. Perhaps there's a way to rewrite the formula to make it obvious that it's strictly decreasing. However you do it, you can just take it as a given if you wish, but it's a good exercise to show that this is strictly decreasing. And that's going to make our proof clear in a moment, because we claim that taken all together, this information tells us that the actual area has to be less than or equal to 1/3. Now, why is this true? We're going to prove it by contradiction. Suppose the area was actually greater than 1/3. So suppose that horizontal line for the area is actually above the horizontal line for the asymptote. Well, because the sequence of right-hand sums strictly decreases, and we know that its limiting value is a third, we know there will eventually be a left-hand sum that is smaller than the actual area. So the way to think about it is this function has to make progress, so to speak, towards the line y equals 1/3. And that means eventually you will find one of these terms below the line y equals a. But that's a real problem, because at that point you will have found a right-hand sum that's smaller than the actual area, but this contradicts the fact that all right-hand sums are larger than the actual area. That contradiction is what proves that a has to be less than or equal to 1/3, because if you assume that a is greater than 1/3, it leads to a contradiction. All right, so let's go back to our picture. Let's divide the interval into 5 equal subintervals again, but this time we'll use the left-hand endpoints to determine heights of rectangles. One thing to notice is that this first rectangle has 0 height. That's nothing to be alarmed about. It's just the way we're doing our approximation gives us a sort of degenerate box that has no area, so we'll have a 0 term. Now, the left-hand sum then will be the sum of these 5 terms. And we're going to recall how we calculated the right-hand sum just a few moments ago. It actually looked like this. Now take a look at those formulas for the left and the right-hand sums. There's really only one difference. It's this extra term that shows up for the right-hand sum, which leads you to believe that there's a very close relationship between these two quantities. So let's actually think about this in generality. Here's a picture of a left-hand sum with n divisions, and here's a picture with a right-hand sum with n divisions. Now please note, we're using 5 subdivisions for the picture because I needed to get a concrete picture, so I had to choose some number of subdivisions. But the argument we're going to use here works in the general case. So there's nothing special about 5. 5 I'm using just for the picture. So here is the cool observation you can make. If you were to push the boxes off to the right here in this picture for the right-hand sum, you'd basically get the left-hand sum, but you'd get an extra box off to the side. And that area of the extra box is 1 over n. So you just kind of let this picture sink in and you realize that what it's saying is that the left-hand sum for n divisions, in this case, is actually just the right-hand sum with n divisions, but you subtract off this extraneous box. So it's a nice little formula relating left-hand sums and right-hand sums. Now why this is useful, if you want to look at the limiting value of the left-hand sum function as n goes to infinity, well, it's just the limit of this difference, and we already know what the limit of the right-hand sums is, and the limit of 1 over n is 0, so the limit of the left-hand sums must also be 1/3. By the way, it's a nice exercise to calculate explicitly the formula for the left-hand sum. We won't really need that formula, but there it is, and you could use it to directly show that the limit as n goes to infinity is 1/3. So here we are. We know that for all n greater than or equal to 1, the left-hand sums in this case are all going to be actually smaller than the area we care about. So once again, the left-hand sums underestimate the actual area for this function on this interval. It's not a general property that left-hand sums always underestimate areas that you're looking for. It's just in this case, it is true. So here's our formula plotted as a function of n, and we're going to summarize the case here. We know that the left-hand sums are always smaller than the area, so whatever the area is we're looking for, it has to lie above this graph. We know that the limiting value of these left-hand sums is 1/3, so here's a horizontal asymptote. Once again, you can convince yourself this is a strictly increasing sequence, and because of this, we conclude that a has to be greater than or equal to 1/3. The proof looks exactly like the proof we used to show that a was less than or equal to 1/3, but instead of decreasing, the sequence is increasing, and so on. So where are we? We know that the actual area we're looking for is both greater than or equal to 1/3 and less than or equal to 1/3. Well, there's only one way out, and that is if a is equal to 1/3. This is kind of a cool moment because we realized that we never actually calculated a directly. We were able to rule out every other possibility, and that only leaves 1/3. This is called the method of exhaustion, and it was actually known to the Greeks, at least, who published their results. So this fact has been known for many, many centuries. It turns out we've put a lot of work into this one special case, but this one special case is really going to carry us the rest of the way. Let's start working our way back to the most general case. The first thing we'll do is, instead of going from 0 to 1, we'll go from 0 to b. What does a right-hand sum look like in this case? Now, the common width of the intervals will be b divided by n. And the arguments we'll need are b over n, 2b over n, and so on. And we will relabel b as bn over n. Here's our right-hand sum. You should check. There are n terms, just as there should be. Each has width b over n, and each height comes from the value of the function at the right-hand argument. There's going to be, this time, a common n cubed in the denominator, but a common b cubed in the numerator. So we can factor out all of that and get a sum of squares. We can apply our sum of squares formula. We can move the n cubed on the inside. And now we have this expression on the right whose limiting value as n goes to infinity is 1/3. So the limiting value of the right-hand sums is 1/3 b cubed. And we also know that for all n greater than or equal to 1, the right-hand sum is still larger than the area we're looking for. Now the left-hand sum is going to be just the right-hand sum, and you're going to subtract off the last box from the right-hand sum. So that's b cubed over n. This is a nice exercise. You can work this out yourself. And from this, we can quickly conclude that the limiting value of the left-hand sums must also be 1/3 b cubed. And we know that for all n greater than or equal to 1, the left-hand sum has to be less than a. So we know a is greater than or equal to 1/3 b cubed, and we know a is less than or equal to 1/3 b cubed, which means the area has to be 1/3 b cubed. Now what happens if we go on an interval from a to b? We'll assume that a is positive, so we're moving left to right, a to b, and we're trying to find this area. And here's the nice geometric fact we're going to use. If you took the area from 0 to b, you could decompose it as the sum of the area from 0 to a and then from a to b. Or, reworking this equation, so to speak, the area we care about is the area from 0 to b minus the area from 0 to a. But these are areas we know how to calculate. This, for example, we know how to calculate. And so the area is going to be 1/3 b cubed, the area of the larger parabolic piece, minus 1/3 a cubed, the area of the smaller parabolic piece that we're going to subtract off. And there's our formula. 1/3 b cubed minus 1/3 a cubed. And so far we've assumed that both a and b are positive. But we claim this formula works whenever a is less than b. So let's just look at this case. Suppose a is negative and we're going to go from a to 0. So by symmetry we can flip this piece over, and this argument will be absolute value of a. And using what we just saw a moment ago, we know that this area should be 1/3 absolute value of a cubed. And that's going to be the same as the area we're looking for. Now we're moving left to right. So what we have to use here is 1/3 0 cubed minus 1/3 a cubed. That's what this formula looks like when a is playing the role of a and 0 is playing the role of b. And we get negative 1/3 a cubed. But in this case, a is negative. So negative 1/3 a cubed really is 1/3 the absolute value of a cubed. And that's the area. We know this works in this case. So what happens if we look at the area from a to b, and a and b are both negative quantities this time? Well, we know that it works in the special case where you go all the way to 0. So we're going to decompose the area we care about as this bigger parabolic piece minus the smaller parabolic piece. So we're going to get, if we apply the formula correctly in the first position, we're going to get 1/3 0 cubed minus 1/3 a cubed, and then subtract off 1/3 0 cubed minus 1/3 b cubed. But you do the algebra, and once again, you get 1/3 b cubed minus 1/3 a cubed. So as long as we're moving left to right, this formula keeps working. And finally, we've got the case where a and b straddle the origin. But this is going to work also. So this area is the sum of these two parabolic pieces. So this first parabolic piece, we'll use the formula we know works there, and the second piece And now that simplifies once again algebraically to 1/3 b cubed minus 1/3 a cubed. Any way you cut it, as long as you move left to right, this formula is going to give you the area under the curve y equals x squared. So there it is. There's our formula. Whenever a is less than b, then the area below y equals x squared, above the x-axis, and between the vertical lines x equal a and x equals b is equal to 1/3 b cubed minus 1/3 a cubed.